Hi everyone, welcome to the regression analysis lecture. This is one of the subjects in the Statistical Science Study Program, University of Indonesia. So, for this session, we will have a look about some regression pitfalls in linear regression analysis. So, some pitfalls that we are looking now is that, about differentiating between observations and experimentation, and then what's the effect of having different type of data in terms of how do we use the regression results. And then later on we will also discuss about multicollinearity, and then about some deviations from the assumption, but for this session we will only consider about the outliers and influential observation, and then we will end up with the parameter estimability. Okay, for the multicollinearity, we will have it in a different session because it's a bit long for this topic. Okay, so now we look at the observation versus experimentation. So, what's the difference between these two types of data? I mean that this data depends on how we collect them. So for the observation is that we just observe, we just record based on what is it, our observation, which means that no control for us over the data. We can't just assign you do this and then let's see what's the effect of doing that. We can't do that. Okay, so only observing. Okay, and this is usually on a social study, and then because we are only observing whatever the phenomenon that we are interested in, then we cannot establish a causal effect relationship because like we don't set up the value like, okay, if I set this to 50, what will be the measurement in B, and then I change it from 50 to 60, then what's the effect on B? We don't do that. So we can't really put a causal effect relationship. Only thing that we can do is to say on the trend that we observe. On the other hand, experimentation is like the complement of the observation. Okay, in observation you have no control over data. In experimentation you have control over data. What we mean by control over data is that you decide on the set up values on which the effects are measured. For example, like I told you before, okay, I want to check on the effect of adding for example, like substance A to this mixture, and then I will see the effect of the amount of substance to the speed of the interaction, or speed of the mm, evaporation of the mixture, for example, like that. And then so you set up, okay, I just put it like the amount of chemical or amount of substance A is like 50 milliliter, and then I add to 60 milliliter, and then I see the speed of the evaporation, and then I change the what is it? Mm, I increase the amount of substance A, and then what is the change in the speed of the evaporation, for example, like that. So you can decide, you can set whatever value that you want to check on the effect. It is very unlikely for the observational study, like in social study, for example, you want to see the effect of kind of like gadget on academic study of high school students, for example, like that. You can't just get a group of students and then you say that, okay, you use gadget for like 20 hours a week, and then let's see the result of your exam, and then you get another group of students and then you say you will use gadget for like 30 hours a week, and then we see the effects on your exam later. I mean that you can't, it's really hard to have control on people's behavior, or uh, like decide on what they have to do or they don't have to do according to our research purpose. So that's why for that kind of study we usually use social what is it of only based on observation. And then while for something that you can do in lab, usually is the science lab experiment, you can always design and set up the value that you want to check. So that's why, because you can set up that and you control other factors that probably can affect the results, you put them under control, then you can establish causal effect relationship. Okay, so that's the main what is it thing that we need to emphasize in here, that is for observational study you can't you can't put causal effect relationship. For experimentation you can establish causal effect relationship. Okay, so what's the consequence in it? That is for us in using the result of the regression. For example, like this, when we do the interpretation of the beta, then for observational study, probably we can just say that, for example, for x1 unit higher, for example, like in this, x1 one unit higher, then we can observe a trend that y is higher or lower. I mean, that depends on the sign of the beta 1. Okay, if beta 1 is positive, then y is higher. If beta 1 is negative, then y is lower. On average, okay, by beta 1 units compared to the lower x. So we can just say, oh, I observe the trend that y is higher or y is lower for x1 that is higher or lower by 1 unit, something like that. While for the experimentation study, you can put like a quite a strong statement. For example, this one, if x is increased by 1 unit, then y is increased or decreased, again depends on the sign of the beta, on the average by beta unit. Okay, so this is like common mistakes that people do in their regression. They put if then statement for interpretation of the beta for the observational study. Okay, so now I want to say that you can't do that. Make it in a more subtle statement, just saying tendency or the trend. Okay, so that's about the observation and experimentation study. Now we move on to the outliers. Okay, so outliers, what is outliers actually? So here the outlier, if in some references, they say that outliers are the observations with the error greater than 3 standard deviation from the predicted value. So here, for example, probably this kind of like a strong candidate for outlier, because this is the observation or the what is it, the exact y value, the exact data here, the point up here, and then point on the line here is the predicted value. So the error or the residual is the distance between the actual value and the predicted value. Okay, we see here two dashed line. Usually this is the confidence interval of the prediction, and it's like plus minus 2 standard deviation from the expected value. And then some points outside this in some references are already considered as outlier, but in some other references it says that outlier is if it is more than 3 standard deviation. So for this example, I think that we can just say this point here up here and this point up here is they are outliers. Okay, so the effect of outliers, we don't want to have outliers actually in our model, because you see that the errors are really big. It's not good for our model's accuracy, and it will also deviate from the assumption of normality. Later on, in further lecture, we will see we will elaborate more on those assumptions. Okay, but we try to avoid having outliers in our model, and that's why if we have something like this, we have to do something to improve our model. This is the second example. So here we have the dots representing the actual data points, and then we have the fit line here for the red line, and then you can see there are some errors, of course, between that is the deviation between each data point to the predicted values, and then we can see here one point up here is like it's really far from the predicted value, so I think that this can be our outlier. Okay, a formal way of testing outlier we will be given in a further lecture. Okay, so again, this is kind of like having this point is a problem for our model, and we will try to find a way to avoid this having this problem. Okay, next, another problem in regression is influential observation. So influential observation is kind of like a bit different with the outliers. In the outliers here we have the regression with the whole data points, and then there are still some points that very far away from its predicted value, and that very far away is set as 3 standard deviation. But then for influential observation, we can see here, okay, we have these data points here. These are 1, 2, 3, 4, 5, 6. And then, so at the first one, I just fit the regression based on 5 data points, and we can see that the regression, the line is close enough to the each of the data points. Okay, seems kind of good um, because this is just using these 5 data points. But then if we look, there's one point here that this point hasn't been included in the model to fit with represented by this red line. This one point here is kind of like showing a little bit kind of like different pattern with the other data points. Okay, so if we include this data point in our model, then it seems like this will affect the model quite significantly. I mean that probably it will change the relationship between x and y, and because it's way down here, then probably I guess that if we put the regression line including this point, then probably we will have the line here. The red line will be kind of like dragged down here. So because the principle of regression line with the ordinary least squares method of estimating the parameter, it wants that the line to be like in the middle of each data points. Okay, so this red line is based on just 5 data points, and then if we put this one point here, then we will have the fitted line is here, the blue one. Okay, so we can see here just because of this one data point, it changes the fitted value. I mean that the beta changes quite significantly. See the slope of the line is decreased quite a lot. So in this case, we say that this data point is an influential observation. And we don't want to have this because, if you compare the blue line and the red line is quite good with those 5 data points. This blue line trying to be as close as possible with the whole 6 data points, but actually, not really good related to compared to with just having these 5 data points. So, we don't have also to have this kind of problem for the influential observation. So my suggestion is that if we have something like this, we need to do analysis of this one point separately, so it doesn't, or what is messed up the already well established relationship like what we have on the graph on the left. Okay, and from here we can see although it already changes, okay, but we can see there's still a big errors here. So we can say this point here, the error is, this the distance between this point and the line, still kind of like a large residual we have for this data point. So we can also say that this data point here is also an outlier. Okay, so influential observation can be an outlier, still based on what is it? Because the residual is considered to be still large enough. Okay. Other pitfalls that we want to establish or we want to discuss now is the parameter estimability. So I took this from this book, Second Course in Statistics by Mendenhall and Sinchich, that the requirements for fitting a p-order polynomial regression model is that the number of levels of x must be greater than or equal to p plus 1. Okay, because you still remember that to fit a straight line, okay, of order 1, then you need 2 data points, right? To fit a quadratic graph or curve, okay, or order 2, then we need a minimum of 3 data points. So if you want to have a polynomial of order p, then you have to have minimum of p plus 1 data point. Okay, but that's only for estimating. But if you want to want to estimate the sigma square, that is the variance of the error, then the sample size must be greater than p plus 1. Otherwise, we can't estimate the sigma square, and then as the consequence, we can't do the model testing. Okay, let's just have a look at the illustration of these things. Okay, so here I already provided some examples. So let's say, okay, so here is the I generated the data. So if you want to see how for the data, we can just say, oops, x not y not okay. Oh, I need to define it as okay. So okay, and then okay. So here, oh, okay, we only have 2 data points here because yeah, I said n equals 2. So this is just to show you having these 2 data points actually. Here, this is the plot of the 2 data points, and then having 2 data points, we can just make exactly one line, right? Passing through the points. So here, if we put the regression, see, we can just get it, and this one line. Okay, let's see. So here we get a perfect line, pass through each of the data points. So we can see, because each data point is on the line, then the r squared should be 1, which means like perfect fit. And we can see here r squared is 1. Okay, but you can see we can't do any model testing, because we can't estimate the standard error, and then the adjusted r squared is also can't be estimated. Okay, so which means that, okay, having fitting a straight line, just to be able to fit the model, yes, you can just use 2 data points, and it will give you kind of like a perfect result, a 100% accurate result. But mathematically speaking, you can say something like that, but statistically speaking, it's just ridiculous to base your model on 2 data points. Okay, so let's say, because the problem is that, do you really believe that you can base your inference just based on information from 2 data points? I don't think so, because probably if you widen your scope, okay, you look for other data, probably the trend is no longer like this. Okay, So it means that more information you gather, then a solid or like a more strong um, what is it way to make decision that we have. What I mean is that let's just look at here. So let's say we have new data. Let's say, okay, I want to add my observation because I don't really believe only on 2 data points. So I gathered 20 more data. And then, so now the new here, I gather more data in addition to these 2 data. And then here I got the result. And then, okay, if we put the regression line here, yes, we can see there are some deviations between what is it, the points and the line. Okay, not perfect like the one that we have in the first one, but still, I think that having more data here, we are more confident that the pattern is really like that. Okay, so just to confirm that, yeah, so it means that the pattern, this kind of pattern is consistent. Now I can proceed with my inference with a bit more confident way. And if we want to look at the result, okay, doing the regression using 2 data points plus 20 more data points. So here we got it. So the R squared here is no longer perfect. Yeah, but we are more confident in using this result compared to the previous one. Okay, so I mean that, okay, this is perfect, and then you add more data, and oh yeah, it confirms that the pattern is like this. So for example, you just try to do the first one, you are lucky at this time because you know the data, the pattern is consistent. But what if, okay, we consider the third scenario here. The third scenario, if for example, like I collect new data, again 20 new data, and then I pull my new data with the previous 2 data points. I put it in different data in different data sets, and then if we look at it, oh, okay, so these 2 points, the one down here and the one up here, they are like the one that we have on this left graph. But then, okay, 2 data points, do you really believe them? And then you try to collect more data, and it turns out that you know the data is like this. And then if you fit the line here, okay, so wow, of course the line should be like this, not just like very steep like in the first one. Okay, and then so again, if you do the regression, we get this result with the R squared is really low here, 0.16. Okay, but in this case, okay, if you have this one still, I would like to use this one, okay, the right one here compared to the left one. Okay, look at the R squared. Yes, the left one has an R squared of 1, a perfect one. The right one has an R squared of 16.48%. But it's because, if we see here, because you know this one data point up here behaves very differently with the rest of the data points. Okay, so in this case, this is an outlier, and then we can just try to exclude it from the model, and if we exclude it from the model, then we will have like a better fit from for our data. So let's see if we just exclude that first data point. Okay, so let's see which one is it. It's the okay, let's see that okay, this is like the mhm, and then let's see view the F2. Okay, so I'll just exclude this one, the first data point. Let's see. Okay, here But just recall the problem with parameter estimability still. R squared perfect, I don't like it. I choose this one, low R squared, because it still represents the what is it the pattern of most of the data. The low R squared is probably just because okay a very big difference for this point, the 1 point outlier here, and then because it behaves differently with the remaining data with other data. So I think it's better to just exclude it from your model and then you report it differently because that's kind of like a special case. Okay, so then let's say I'll have new data point is that df2 minus 1. Let's see. Okay, it means that I just exclude the first data point and then here I just use my data is df3. So in this case, and then if we have this one, data equals df. Oh yeah, it's alright. So here we can see that it's a bit when we exclude this 1 point, there's an increase in the R squared, which means that the model is kind of like what is it improved. And in here we can just let's say data equals the F3 and color is blue. Okay, so if we put like new regression line not including this data point, we can see that the regression line is changed as well. So we can say that related to our previous discussion on some other problems, this point up here is an influential point because it changes the equation, and also it is still an outlier because the error is still very big in here. Okay, but then going back to the example, this is just to show you again, although the R squared is like really small in here, 21.24%, but I still believe this model better than just doing the inference based on the result from the model with just two data points on the left here. Okay, so this is a second example that is I just generated three data points x and y here, and then this is based on a quadratic term. So then if we put fit the regression, okay, quadratic regression x and x squared here, using those three data points, of course, again, you will have a perfect R squared. Okay, R squared of 1, which means that each data point will be on the fitted line. But again, statistically speaking, it is just doesn't make sense if you want to use this model, the equation here, to do your prediction or your to do your inference, because again we can't really rely on really small sample size. Okay, so I think that's all that for this session on the some regression pitfalls. Later on we will discuss more about the multicollinearity. Thank you.